This is the Earth that is rotating around its center of mass. In other words, it is spinning, and we want to find the speed at which it spins to see how fast a point on the surface of Earth moves. The radius of our planet is about 6,378 kilometers, and it takes the Earth about 1 day to experience a full rotation, which is approximately 86,164 seconds. Angular velocity is a measure of how fast an object rotates or spins around a fixed axis. It tells you the angle an object covers per unit time. In the case of this rotation, we are talking about this axis. This is the formula by which we can find the angular velocity of the Earth. It means that the Earth covers 7.292 times 10 to the power of minus 5 radians per second. Now we can easily find the speed of a point on the surface at the equator, which yields 465 meters per second or 1,674 kilometers per hour, 20 times faster than a car in a highway. Right now you are moving at this speed and you just don't feel it. We usually feel acceleration and not speed, like when we are in a car or on an airplane. The funny thing is that if the Earth suddenly stops spinning, you will still move at this speed and everything on the surface of the Earth would move at this speed and there would be a chaos on Earth. If we suppose that an electron is spinning like the Earth, we face a speed that violates the laws of physics based on Einstein's theory of relativity. We know that nothing can move faster than the speed of light, but considering an electron to be a sphere-like, Earth causes such a problem, and that's why you shouldn't think of an electron as a spinning sphere when we talk about spin. Actually, a spin is an intrinsic property of some particles that is a purely quantum concept, and there is no classical equivalent. An intrinsic property that causes particles to interact with magnetic fields. So, spin is another observable we need to deal with in quantum mechanics. And we know that for each observable, we can associate a Hermitian or self-adjoint operator, meaning that the complex conjugate of the operator is the same as the operator itself and yields real values when acts on a state. The other important thing we need to know about these operators is their commutation relations, which show how the order of using them affects our measurement of the state of a system. In fact, it shows if there would be an uncertainty in measuring the two observables at the same time. For example, the commutation relation for the total spin squared and the z component of the spin is 0. It means that we can measure them at the same time, and it also means they can be represented by the same kets. Algebraically speaking, when the total spin square operator acts on these kets, we have this eigenvalue relation. And for the z component of spin, we have h bar times m as eigenvalues of this operator. The possible values for s can be integers or half integers. In particle physics, the spin of bosons like photons and Higgs boson is integer values, and the spin of fermions like electrons, protons, and quarks is half integer values. The possible values for m depend on the values of s, which is fixed for each kind of particle. For example, spin 3/2 has 4 values for m, which are minus 3/2, minus half, half, and 3/2. There are two other operators we are going to be dealing with in this video to find the states associated with the x and y components of spin angular momentum. These are called raising and lowering operators, which we use to manipulate m in the ket using the simultaneous kets we talked about earlier. Pay attention that here I have used ms to show that this number is associated with spin angular momentum. For orbital angular momentum, we use ml. If you want to know how we came up with all of these relations, I suggest that you watch this video later. But now we are going to talk about spin half, which is a very common case, and also Pauli matrices that are used to represent the spin operator. For a spin half system, we have two values for m, which are the possible projections of spin angular momentum on the z-axis. So there are two possible states for a spin half system, which are also represented by up and down cats like this. Let's use these two relations to find the eigenvalues of s squared and sz. This yields 3/4, s is half, and m is plus or minus half. So the eigenvalue relation for the total spin squared is 3/4 times h bar squared times the same cats. And the relation for the z component of spin is plus or minus h bar half. Geometrically speaking, this is the magnitude of our spin angular momentum, but we don't know the magnitude of the components at the same time. I know it's weird, but this is a quantum property that obeys the uncertainty principle, and in quantum world, uncertainty is the new normal. However, we know that the projection of the spin on the z-axis is h bar half. In this framework, we know nothing about the magnitude of the x and y components. We can also find this angle using inverse cosine of the magnitude of the z component divided by the magnitude of a spin, which is about 55 degrees for the case of spin half. We are going to use these two relations to find the matrices that represent the operators associated with spin angular momentum. We are looking for a 2x2 matrix because we have two eigenstates. There are 4 elements that form this matrix, which are constructed by simply acting the operator on each ket and finding the inner product using different bras. These two are 0 because when s squared acts on the ket, doesn't change it, and the inner product of the two different cats is 0. But the two elements on the diagonal are non-zero and equal to 3/4 times h bar squared. We can simplify it using 3h bar squared divided by 4 as a coefficient of a matrix, which is clearly an identity matrix. We can do the same thing for the operator related to the z components of a spin. Again, there are two 0 elements because sz doesn't change the cats, and there are two non-zero elements on the diagonal, one of which is negative because when sz acts on minus half, it creates a negative sign. So we have another beautiful matrix, which is obviously not the identity matrix, but with non-zero elements on the diagonal. To find the matrices that represent the x and y components of a spin, we can use these relations for raising and lowering operators. We need to pay attention that these operators change the cats, and so we expect some matrices with 0 diagonals. For both raising and lowering operators, this term is 3/4, and the second term is either minus 3/4 or a quarter, which yields 1 when added to the previous one. These are the 4 elements of the raising operator matrix. These two elements are 0 because the operator changes the second ket, and the inner product would be 0. This one is also 0 because when the raising operator acts on the upper bound, which is the state with magnetic number half in this case, it yields 0. This is the only non-zero element of this matrix, which is h bar. So our raising operator looks like this in terms of matrices. We can do the same thing for the lowering operator. These 3 elements are 0, and this is the only non-zero element. This is the corresponding matrix for the lowering operator. To find the x component, we can add the 2 operators we just talked about, and for the y component, we can subtract them. Pay attention that in the last step, we have used this identity. We can use 2-element column matrices to represent the state of a spin-half particle. These are a specific type of mathematical object called spinors, though we won't discuss spinors in full generality here. Importantly, a set of such spinors can form a complete orthonormal basis, allowing us to span the entire Hilbert space for the spin degree of freedom. We can easily show that these eigenvectors form a basis that is complete. We can also show that they are orthonormal. These are the matrix representations of the 3 operators for the spin-half system. They have a common factor h bar half and some 2x2 matrices. These matrices are called Pauli matrices and are denoted by sigma x, sigma y, and sigma z. Multiplication of these matrices with themselves gives the identity matrix. And if we multiply different Pauli matrices, we get the other one, as you can see in these equations. If the order of multiplication is like this, we get a positive I as coefficient for the other matrix. This is an even permutation. And if the order of multiplication is opposite, we get a minus I as the coefficient, and this is called an odd permutation. We can show this permutation with this symbol, which is called the Levi-Civita symbol. If we have an even permutation, it yields 1. For odd permutation, it gives -1. And if two of the indices are equal, it gives 0. We also need another symbol for the multiplication of the same matrices. If they are the same, we want it to be 1, and if they are different, we want the outcome to be 0. This is the definition of Kronecker delta. For the multiplication of these matrices, we can use these symbols and write it as the sum of a Kronecker delta times the identity matrix and a sum over the third index L. In this kind of notation, instead of x, y, and z, we usually use 1, 2, and 3. For example, let's calculate the multiplication of sigma 1 and sigma 2. The first term is 0 because j and L are not equal. And in the second term, which involves a sum over L, the only non-zero term is 3 because when L is 1 or 2, there will be a repetitive index which makes the Levi-Civita symbol become 0. So the answer is sigma 3 or sigma z. In this example, again the first term is 0, and in the second term the only non-zero L is 2, which makes an odd permutation leading to a negative sign. So the answer is minus I sigma 2. In this case, on the other hand, the first term is not 0 and the second term yields 0 because in the Levi-Civita symbol we have two 1s. So the second term vanishes and the answer is the identity matrix. We can also find the anti-commutator of these Pauli matrices by using the definition of multiplication. These two terms are equal, so we double it. Look at the second and fourth term. In the fourth one, the order of j and k is different, so it creates a negative sign because the permutation has changed. So these two terms cancel out. For the commutator of the two matrices, we have the same relation but with a negative sign. It causes the term with identity matrices to cancel out, which leaves only the term with Levi-Civita symbol. There's something cool about these matrices. When we also include the identity matrix, we can express any 2 by 2 complex matrix as a linear combination of these four matrices. The coefficients are complex numbers, and to find the coefficients, we can expand the matrix using our matrices and their linear combination, which transfers it into a 2 by 2 matrix. Now we can easily compare it with the first matrix and find the coefficients. Let's find the coefficients for this matrix. They are 3, 1, -1, and 1 respectively. And our matrix can be written as a linear combination of Pauli matrices and the identity matrix. Now, suppose that we have a spin half particle which is in the state of psi. This state can be shown using all of these forms you can see, which are different representations of the same concept. These are the eigenstates of the z component of the spin operator, which we can use to express any state we want in these bases. These are the eigenspinors we use to represent these states. We can use these states and their orthonormality to investigate different concepts related to a spin of the particle. The modulus of a squared is a real number that shows the probability of finding the particle in a spin-up state. And similarly, the modulus of b squared shows the probability of finding our particle in a spin-down state. Pay attention that a and b are complex numbers, and to find the magnitude or modulus, we just need to multiply them with their conjugates. We either expect to find the particle in a spin-up or spin-down states. So the addition of these two probabilities has to be 1. We can also write the eigenvectors of the x and y components of the spin operator using the eigenvectors of the z components. We can use the Pauli matrices and multiply them with these eigenvectors, which are represented as eigenspinors now, and confirm that these kets are the eigenvectors of the x component of a spin operator. If you want to know how we can come up with these states, we can start from the Pauli matrix representation of the x component of the spin operator and then first solve the characteristic equation that involves lambda to find the eigenvalues. Then, by using these eigenvalues, we can find the possible eigenvectors. We can do the same thing for the y component. First, we solve the characteristic equation. It yields plus or minus h bar half as we expected. Then we choose a general spinner with alpha and beta as the elements we are looking for. We act as spin operator on this ket to find a relation between alpha and beta. This is what we get. If we choose alpha to be 1 divided by square root of 2, beta yields plus or minus I divided by the square of 2. And these are the eigenspinners or eigenvectors or eigenstates of the y component. Now suppose that this is a spin half particle in the general state of phi. We want to find the probability of getting plus or minus h bar half if we measure the x or y component of the spin. First, we expand the state phi based on the eigenstates of the x component. The next step is to find C1, which can be calculated by multiplying phi with the positive eigenstate bra. It yields a plus b divided by root 2. C2 can be calculated by using the negative eigenstate, which becomes a minus b divided by root 2. The probabilities of getting plus or minus h bar divided by 2 can be calculated by these relations. We know that the sum of these two probabilities should be 1, so we add them. Then expand these two terms, which are complex numbers, but the complex parts cancel out and we are just left with the real numbers, which yield 1 because phi is a normalized state. We can do the same thing for y by expanding the state in terms of eigenvalues of the y component of the spin. Again, we can find the probability p plus and p minus. And if we add them, the answer would be 1 as we expected. So far, we have just talked about the spin angular momentum in 3 directions along the x, y, and z axes. The question you might ask is how we can find the component of spin along an arbitrary direction r hat. This is the unit vector in a spherical coordinate along this arbitrary direction. The dot product of these two vectors gives the component we are looking for. Let's call this component SR, which is a matrix, and we want to find it. The first step is to write the Pauli matrices in their matrix form, and this is the matrix we are looking for. Take a moment and see how we came up with the different elements of this matrix. What do you expect the eigenvalues of this matrix to be? Obviously, again, we expect them to be h bar half, exactly like Sx, Sy, and Sz. To find the eigenvalues, we first need to find the answers to the characteristic equation, which is a determinant including lambda. Pay attention that we need to include the coefficient h bar half in the determinant. And again, as we expected, the eigenvalues are plus and minus h bar half. Now we are going to find the eigenstates for the two eigenvalues. Let's call them psi r plus and psi r minus. We choose an arbitrary column matrix with elements alpha and beta, and we want to find a relation between them so we can find our desired eigenspinners. The first line gives this. And now we have a relation that relates beta and alpha. For the upper sign, which is positive, we can use these two half-angle trigonometric equations. After using these trigonometric identities, we get this. Our eigenstate has to be normalized, so modulus of alpha squared plus modulus of beta squared has to be 1. We choose alpha to be cosine of theta half and beta becomes e to the I phi times sine of theta half. And our first eigenspinner is this one. For the lower sign, which is negative, we need these trigonometric identities. This is beta, And the normalization condition gives us this relation based on which we can choose proper alpha and betas. We choose alpha to be e to the I phi times sine theta half, and beta becomes minus cosine of theta half. And now these are our two eigenspinors for the spin in an arbitrary direction.